Welcome to NHP's public webinar platform, where in these challenging times, NHP is leading the industry in adopting alternative customer engagement and training methods. Today, we will expand on the information provided in our first webinar on this topic. If you missed the prior session, I recommend that you go to channel NHP on YouTube to access this and many more informative webinars. As we're only taking approximately 30 minutes at a time, this will be the second in a series of 4 on selectivity. The topic seems a simple, straightforward one. However, when we look at selectivity in all its levels and definitions, it can be a very complex subject to understand. This webinar covers the basic to intermediate aspects of circuit breaker selectivity and cascading. We'll briefly recap session 1. We will also look at the regulations according to AS NZS 3000-2018. We will explain the meanings of selectivity and cascading, including some of the expected behaviours of the protection, discuss how circuit breakers operate and how to modify their time current curves. We'll explain current limiting and the 3 methods used in determining how selectivity is achieved, and how in practical terms molded case circuit breakers, miniature circuit breakers and fuses operate under these conditions. We'll discuss the current limiting characteristics of circuit breakers and fuses and how they operate in fault scenarios, providing backup protection for auto and non-auto devices. So why achieve selectivity? If we use it smart, it can give us a possible reduction in costs in commercial and industrial applications by providing possible reductions in switchboard sizes and real estate, and an increased reliability of supply. It can also assist in finding the root cause of faults or anomalies in the system. Better system reliability. The diagram left of screen depicting lack of selectivity shows a fault on a single circuit could plunge the whole site into darkness. This means a fault on one circuit could cause the main breaker A to trip, causing the whole site to shut down. The diagram right of screen depicting circuit selectivity shows that a fault in the system will only affect the circuit where it originates. All other circuits will remain on, meaning supply to the rest of the site is unaffected. Ramifications of unnecessary power outages can range from annoying to dangerous. The monetary costs alone could range from zero to many millions of dollars depending upon the nature of the industry and processes shut down. Why achieve selectivity? Easier fault finding and less downtime. As we've seen in the last slide, without discrimination, it is possible that a fault on a downstream circuit could easily cause the upstream breaker to trip. If this were to occur, fault finding could take a long time, as each individual sub-circuit would need to be checked to see if there was a fault on that circuit and what the fault was. If it was an intermittent fault, or in fact a motor start or overload that isn't present when no power is supplied, it could take considerably longer to find. With selectivity, only the circuit that is having problems should trip under the fault, which means only one circuit will need to be investigated. It is not only the issue of loss of power in these instances, the time taken to safely investigate the root cause, rectify the potential fault, and reinstate the supply may cause process delays, cause quality control issues, and potential wastages, as well as possible data loss because of inadequate backup systems such as UPS providing ride-through or backup power. In the case of equipment such as transfer switch operation, an upstream circuit breaker trip would cause a system lockout and deny backup transfer switches from closing onto a potentially faulty circuit. So let's recap on what selectivity is in general terms and at its most basic level. We see here time and current graphs for thermal-magnetic breakers, electronic circuit breakers, and fuses. Time is ascending on the y-axis, current is ascending on the x-axis. This means that lower current levels take a longer time to trip the protection device, hence the term long time, trip or setting. This is provided by thermal protection on thermal magnetic breakers or long time setting on electronic breakers, IN nominal rating or IR as adjusted trip rating. High current takes a short time to trip, referred to as short time delay setting on electronic breakers. Thermal magnetic breakers do not have this specific time delayed setting function. Extremely high current has virtually instantaneous tripping effect on the protection device, provided by the magnetic setting on thermal magnetic devices and the instantaneous setting on electronic devices. Depending on the IN or IR current of the device will depend on what the actual current levels are to cause a trip in any of these regions. AS NZS 3000-2018 refers to reliability of supply or discrimination, specifically in clause 2.5.7. It refers to coordination of protective devices and states that coordination of these devices needs to consider both discrimination, selectivity, and backup protection, cascading, to operate correctly. It states the rule that where two or more devices in a series arrangement with a load or circuit, then in the event of a fault, the downstream device shall operate for a given fault, while protection devices upstream shall not operate. This is understood to be true up to a nominated level from the standard or by an agreement with the end user. Backup or cascade operation depends on the characteristics of the two devices as well as the comparative behavior of the two devices when sharing the same level of fault current. This includes their behaviors from energy let-through and the peak current withstand of the downstream device, as well as the let-through characteristics of the upstream device at this level of fault. The standard very importantly states that manufacturer's instructions data should be used where available. Manufacturer's technical data. AS NZS 3000-2018 continues to say that discrimination, selectivity, is achieved using a discrimination study or the manufacturer's data and tables or the comparative current ratios shown in the standard. Major equipment manufacturers go through extensive testing of combinations of circuit breakers to identify and publish selectivity values, and the latest revision of AS NZS 3000 mandates the use of this data on all circuits where the downstream breaker is greater than or equal to 800 amps. Manufacturer's data can be presented in different formats, but essentially the enhanced selectivity and cascade levels for tested combinations of breakers are published. In tables provided by NHP, selectivity level of the combination appears first, and the cascade level of the two devices appears second. These tables state the maximum level of fault for which the breakers will display a particular behavior. Where both selectivity and cascade levels are shown as the same figure, this simply means that this is the maximum permissible level that this combination of devices has been successfully tested to. The expected behavior is selectivity between the devices. The thermal magnetic molded case circuit breaker has adjustable thermal settings, IR, and magnetic settings, II. The thermal dial numbering depicts a percentage of the nominal current, and the magnetic represents a multiple. The thermal trip function is achieved by a bimetallic strip bending in proportion to current produced heat to press on a trip release latching mechanism. This is of course heat dependent and is proportional to current. It is sensitive to ambient temperature and will trip more quickly in warmer environments. The magnetic protection is provided by the magnetic short circuit coil, which at certain high current levels will force an internal ferrous shot pin out against spring tension to trip the latch mechanism. In the standard AS NZS 60947-2, this type of breaker is referred to as Category A. Thermal magnetic breakers are the cost-effective option. Because of their characteristic and limited adjustability as well as their total reliance on magnetic structure and dynamics, they should not be used upstream of other thermal magnetic molded case circuit breakers if high levels of selectivity are required. Their wide tolerance band and susceptibility to setting drift due to ambient temperature conditions surrounding the breaker means tripping time may vary greatly. Thermal magnetic circuit breakers are best suited as the final distribution breaker upstream of miniature circuit breakers and RCBOs. Electronic molded case breakers have a number of setting style options available. They generally offer a wider range of setting options than thermal magnetic types, and this allows for the finer range of setting adjustments that are often required. They also introduce the short time portion of the curve to allow improved selectivity with thermal magnetic breakers and fuses downstream. Some electronic OCRs feature preset curve shapes based on typical applications you can simply alter with the IR settings. These are achieved with two setting adjustment dials. Other OCRs, or overcurrent relays, features 5, 6 or 7 dial adjustments as well as fully adjustable OCRs featuring full access to the setting register via LCD screens and digital adjustment tools. So let's look closely at discrimination, the definitions, and what it brings. Partial discrimination may occur when the time current curve of the downstream device overlaps that of the upstream device beyond the selectivity level nominated. This means that there may be conditional restrictions on the level required to be achieved. This may be determined against the prospective fault level at the downstream device or the braking capacity of the downstream device. In this example, we see that the prospective fault current at C2 is 40 kA, whereas selectivity is only achieved up to 36 kA, partial discrimination. Full discrimination, or total discrimination, is generally nominated up to the prospective fault level of the downstream device or the interruption capacity of the downstream device. Full discrimination can be achieved provided the time current characteristics do not overlap. In reality, the lowest horizontal section of the graph shows that they do overlap. This region is the test or reflex region, where breaker behaviours are somewhat unpredictable and less combinations are tested. Determination of compatibility between circuit breakers is where we arrive. And in this instance, we can see that for a prospective fault current of 30 kA at C2, full selectivity is achieved. Enhanced discrimination is achieved when C1 remains closed, when, for example, C4 clears a fault that is higher than its ultimate limit, ICU or ICN. The upstream device shall not trip up to a nominated level above the downstream device's tested short circuit capacity. Some of the physical actions of the upstream breaker exhibit current limiting behaviour of cascading, however to a lesser extent and for a shorter time. This ensures that the breaker does not actually trip. This action enhances the braking capacity of the downstream device beyond its tested limits while still achieving selectivity to this high level. So in reality, how does fault current limiting occur? Firstly, the device design relies on the dynamics involved with magnetic repulsion. We see here an illustration of Fleming's right-hand grip rule, whereas the thumb indicates the direction of the current and the curled fingers indicate the direction of the magnetic force, or specifically in the AC circuit, the magnetic flux, as it's constantly fluctuating in strength and direction due to the 360-degree rotation and the direction of the current constantly reversing with the 50 cycle per second frequency. So think of the flux direction, force acceleration and deceleration as you would observing, say, a top-loader washing machine agitator. Imagine two machines side by side, the central spindles being the conductors And if we place two conductors carrying the same source of current next to each other, but the current directions oppose each other, the magnetic flux forces will also oppose each other with forces that proportionally correspond to the value of the current at any given time point on the current sine wave. In practical terms, the current limiting circuit breaker design relies on this area of physics to enhance its effect in the system under high fault conditions. The contact set, in some cases U-shaped contacts, in others specifically designed contact arrangements to amplify the effects, they are designed so that under normal current carrying, overload, and events such as motor locked rotor currents, the magnetic forces are not high enough to actually force the contacts apart. Under short circuits at a medium to high level, the contacts will be forced to separate momentarily. The current will continue to flow through the arc between the contacts, but this arc impedes the rise in current in the circuit, thus lowering the rate of rise of current and gives time for the downstream device to open at a lower fault current level than might normally be the case. As the two breakers acting in unison create the conditions where the current is limited in magnitude and the duration of the entire interruption process is shortened in total clearing time, the peak current may be limited and the let-through energy is lessened by the shortening of the current flow duration and the peak of the current value. This action minimizes the mechanical and heat stresses on the conductors in the circuit. Determination of selectivity can be assessed using a number of different methods in a number of different levels. Apart from the testing methods used by manufacturers as a proven outcome, assessments can be made using time current curves, the determination at a low level of current, peak let-through curves, and energy let-through curves for higher end fault currents. These methods can be of help in refurbishment, such as brownfield sites, and additions to systems where assessments need to be made between dissimilar models or untested combinations. Time current selectivity is fairly straightforward up to the highest current point of the downstream device, as long as it does not overlap the upstream device's curve. This is the most commonly used method conforming to AS NZS 3000 requirements. Current selectivity. For applications of higher risk, current selectivity is a method of using peak let-through current graphs of individual circuit breakers to determine compatibility. In reality, this method is applicable in a limited number of applications where fault levels are not very high. The graph on the right depicts the difference in the peak value to the RMS value. AS NZS 61439 defines an N-factor multiplier for peak current over RMS current depending on the RMS prospective value. The peak, or N-factor, reflects the value of the distorted asymmetrical DC peak when a high short circuit current is initiated. The diagram shows us that for an x-axis we show ISC, which is short circuit RMS, and on the y-axis the I peak, being peak asymmetrical. For any short circuit fault current, we can determine the absolute peak current that this circuit breaker may let through before clearing the fault. The peak current let through is often higher than the value of the prospective symmetrical fault level, depending on the breaker and the fault level at the instant of the fault being initiated. The peak let-through current curves allow us to determine if the level is less than the instantaneous setting of the upstream device. The peak let-through allowable for any particular pair of devices can be determined for any fault current level based on these graphs and settings of the upstream device. Energy selectivity. Energy selectivity compares the let-through energy curves of the downstream device to the tripping initiation curve of the upstream device. For any given fault level, the downstream breaker will let through an amount of energy in amperes squared per second, or I squared T. It's depending on the time taken for the breaker to open and the current limiting nature of the breaker. This was previously used to determine the compatibility of fuses based on their pre-arcing and total clearing time, one compared to another. I squared T. Discrimination is achieved when the let-through energy of the downstream device is less than the energy required to unlatch the upstream device. The diagram on the left depicts the two devices in series where for a given prospective short circuit current, the total clearing value of the downstream in green is less than the pre-arcing value of the upstream device in black. Therefore, energy selectivity is achieved. Conversely, the right-hand diagram shows the downstream breaker, in green, still in the process of clearing the fault while the upstream device threshold has been reached and it's started to unlatch, therefore not guaranteeing energy selectivity to the full nominated level. This may be an unreliable pairing of devices for this application, as the upstream device may go on to open and compromise reliability of supply. Fuses are very effective fault current limiters suitable for some applications, especially where fault levels are high and sub-circuit current values are low. The current limiting fuses operating in their range will limit the maximum instantaneous peak current within the first half cycle to a value substantially less than if the fuses were not in the circuit. The peak value is almost always well below the prospective RMS value, and the energy let-through is also minimum. The compromise is that the fuse always needs to rupture or blow to deliver the result, and as a consequence will interrupt power to all circuits downstream. Chart indicates the extent of the backup protection afforded up to 65 kA for as little as a 6 kA device. Finally, let's take a look at non-automatic devices, i.e. devices that have no trip function or the trip functionality has been disabled. This group includes isolators and load break switches, as well as non-auto circuit breakers. In the case of non-auto multi-case circuit breakers, they have relatively low short circuit withstand capacity because essentially the construction of the device was designed with trip mechanisms in place to quickly interrupt faults, not to remain closed under fault conditions. Standard multi-case circuit breakers can be used to provide protection for the same construction non-auto models, as well as for certain isolators and for load break switches, etc. Multi-case circuit breakers can also be used very effectively where automatic transfer switches are being used that do not incorporate overload and short circuit protective functions. Coordination charts are published by most premier and tier 1 manufacturers and vendors. In summary, AS NZS 3000-2018 simply nominates the minimum level of supply security required to ensure the system is functional and security of supply is maintained at a practical level. This leaves much of the expectation of nomination of selectivity levels and system behaviour to the end user or system designer/installer. This second presentation is built on what we covered in our first webinar on this subject. Here we demonstrated some basic to intermediate information and scenarios. We've reviewed basics of selectivity and cascading, explained in practical terms how it is achieved using multi-case circuit breakers, both thermal, magnetic and electronic, as well as miniature circuit breakers and fuses. We've covered current limiting characteristics of devices and how they behave in fault scenarios, providing backup protection. We've explained the three main methods of determining how selectivity is achieved and how in practical terms, multi-case circuit breakers, miniature circuit breakers and fuses operate under these conditions. We've also covered the current limiting characteristics of circuit breakers and fuses and how they provide backup for auto and non-auto devices alike. Future webinars on this subject will become increasingly complex and challenging. We trust you are able to gain some information from this second in the series and look forward to you tuning in to our future webinars on this subject and others. Please type your questions into the dialog box along with your email address, and these will be immediately followed up and answered via return email. I hope you found it beneficial today, and if you'd like to watch this again or to find more webinars in this series, please go to nhp.com.au or our dedicated NHP YouTube channel. If you have any further questions about this webinar topic or others, please contact your local NHP sales representative. With smarter and faster decision making and seamless connectivity spurring new collaboration, NHP is enabling the connected enterprise.